So here's a fun word, saponification, from the Latin, soap. This is how soap is made. From a chemicals perspective, we can call it ester hydrolysis. And again, hydrolysis means we're using water, or H2O, to cut something. All right? Here's our ester. Let's say we treat our ester with sodium hydroxide, good old lye, caustic lye. Okay, identify the nucleophile, identify the electrophile. My nucleophile is my electron-rich oxygen, so hydroxide. My electrophile is that carbon. That's going to be where I want to have my OH go after. You can imagine two mechanisms by which I can break down this tetrahedral intermediate to get to my product, this carboxylate ion. And I think that both of these mechanisms are reasonable. Usually, I think about my OCH3 and my OH are essentially the same in terms of how good of a leaving group they are. If I think about the pKa of methanol versus water, they're essentially the same pKa for the acid, so the same basic strength. So I think that it's about a horse's chance, or a horse apiece, that I'm going to either lose OH and go backwards or lose OCH3 and go forwards. As soon as I go forwards, though, I'm making an acid. This proton is now very acidic, and remember, I'm in base. So as soon as the first molecule of base finds this pretty acidic proton, that is going to do an irreversible deprotonation, right? The pKa difference here is 10 orders of 10 different, right? The pKa of water is 15, the pKa of the acid is 5. So this is going to be really fast and irreversible to get to this anion. If you don't like the thought of forming an acid in base, then you could imagine that another molecule of OH deprotonates this, and I get to some dianion over there. And once I'm there, now I only have the one leaving group, the OCH3, and once that leaves, again, that's a more or less irreversible reaction now because this is too electron-rich to get attacked by some nucleophile. So in either case, I am hydrolyzing this, but it doesn't stop at the carboxylic acid. It keeps going in base all the way to the carboxylate anion. And by doing so, it is irreversible no matter how we think about this last step. So there's no way that I can get back from the carboxylate to the ester, which is to say, I cannot start with the carboxylic acid, give it, say, methoxide, and go to the ester. That won't work. It won't work because all this is going to do is do a very, very fast acid-base reaction to get to the carboxylate and methanol. Okay? So I cannot simply take carboxylic acid and treat it with O- to get an ester. But I can get to an ester, from an ester to the carboxylate ion irreversibly. I mentioned this is how soap is made, saponification. Here is more detail on that. So this is an example, a rough sketch of a fatty ester, all right, a triglyceride. So I've got long carbon chain fatty acids here, oxygen, and then a 3-carbon unit that will eventually, that's where the glyceride comes from. When I take animal fat or any kind of triglyceride and react it with OH-, I'm going to attack the carbonyl, all of these eventually, get my tetrahedral intermediate, and then collapse this down to break that ester bond. So what I'll end up with at the end of the day is a lot of glycerol, which maybe I can use, maybe I can't, and a lot of this sodium salt of this fatty acid. And this is what soap is, and what natural soap is. It's the salt of some fatty acid. So if you've ever seen Fight Club, this is when they make the soap out of the fat. This is how that works. Okay, so this is sometimes called ester hydrolysis. It's sometimes called saponification because this is the old school way to make soap. You hydrolyze the fatty acid ester with caustic lye, sodium hydroxide, that makes a tetrahedral intermediate that then breaks down, and I end up breaking these bonds to get glycerol by itself and 3 carboxylates. Concentrated sodium hydroxide, caustic lye, will hydrolyze amides under basic conditions. So treating this with concentrated NaOH, probably in boiling water, is going to give us this carboxylic acid. How should we think about this working? Okay, again, whenever you step up to a reaction, we want to identify the nucleophile and identify the electrophile. If we're in basic conditions, that always means that we have a really reactive nucleophile and probably a not very reactive electrophile. So this is our nucleophile, OH-. It's going to react with our electrophile there, and we get some tetrahedral intermediate. From here, now we say, okay, what's my better leaving group? Is it O- or is it N-? Whichever the better leaving group is going to leave. So when I look at that, I know that O- is way more stable than N- because O is more electronegative. Another way to say that is that N- is a much stronger base than O-. And so when I look at this, I say, I'm sorry, I'm not going to go forward. I can't lose this and not that. But if I've got a lot of base around, this OH is still a little bit basic. And so, this OH is a little bit acidic. I can imagine another molecule of hydroxide coming in to deprotonate it. And that gives me kind of this weird looking intermediate. So now I don't have 2 leaving groups. I'm not going to kick off atomic oxygen 2-. That's not going to happen. Right? So no matter how bad of a leaving group this is, it's still better than that. So I will, at this point, lose N-. Is it likely? It's not very likely, but it'll happen enough times that I will get to the carboxylate and this very, very strong base, which will take the closest acidic proton to it, which is going to be water. So as soon as this thing sees a molecule of water, it's going to grab a proton from it, and so we'll end up with this plus that. Okay, so again, this requires some forcing conditions. I'm going to have to use some heat and probably some pretty concentrated base catalyzed amide hydrolysis.